Module 8, Lecture B, Scaling Practices. By the end of this lecture, you will be able to apply gradient accumulation and effective batch size strategies in distributed training setups, combine mixed precision with DDP to improve throughput while maintaining convergence, and implement basic logging and checkpointing that work correctly in multi-process environments. Scaling batch size, effective batch size math. In distributed training, the key idea is the effective batch size, which is the total number of samples that contribute to a single optimizer update across all devices and accumulation steps. On a single GPU, this matches the batch size. But with multiple devices and gradient accumulation, each device processes its own mini-batch, and their gradients are combined before updating the model. This combined size determines how the optimization behaves, how stable training is, and how you should tune hyperparameters such as the learning rate. Understanding effective batch size is therefore essential when scaling training across multiple GPUs or machines. When training a model on multiple GPUs, each device processes its own small batch of images, and their synchronized gradients together act like a single larger batch. For instance, if 8 GPUs each handle 32 images, the combined gradients reflect information from 256 images. You can simulate an even larger batch without using more memory by accumulating gradients over several of these synchronized steps before updating the optimizer. If you accumulate over 4 iterations, each optimizer update effectively uses gradients based on 1024 images. This makes the optimizer behave as if it were training with a much larger batch, which influences gradient variance and how the model converges. When scaling up training, the key is to match the effective batch size of the original setup. If the reference uses a large batch on a powerful accelerator, you can reproduce this by spreading smaller batches across multiple GPUs and using gradient accumulation so that each optimizer step still sees the same total number of samples. For example, several devices can each process a smaller local batch over multiple iterations before updating the weights. By tuning the number of devices, the local batch size, and the number of accumulation steps, you control the effective batch size and help preserve model quality and convergence behavior. Accumulation loop patterns. When moving from single device to distributed training, gradient accumulation becomes especially important. Instead of updating the model after every mini-batch, each process, usually on its own GPU, runs several forward and backward passes, adds the gradients together, and then performs a single optimizer step. You choose an accumulation window, such as 4 or 8 mini-batches, and only update the model after all those gradients have been collected. This synchronized accumulation across processes lets you effectively use larger batch sizes across multiple devices. In distributed training, it is essential to align gradient accumulation with gradient synchronization across all processes so the model updates are correct. During each backward pass, gradients are typically averaged across devices, so every accumulation step already reflects data from all processes. This ensures that each process performs the same number of accumulation steps before the optimizer updates the weights. As a result, the effective batch size becomes the mini-batch size multiplied by the number of devices and the number of accumulation steps, such as when training on 8 GPUs and accumulating gradients over several iterations to maintain a stable batch size. In distributed training, you often need to adjust how you accumulate gradients to handle uneven dataset sizes, changing sequence lengths, or varying input resolutions. For example, in language tasks, you might group sentences by length, which changes how many tokens appear in each mini-batch. So some practitioners trigger optimizer updates after a target number of tokens instead of a fixed number of batches. In memory-limited settings, such as training large vision transformers, You might also change how many steps you accumulate when the input resolution changes. The crucial point is that all processes must follow the same consistent rule for when gradients are accumulated and when updates are applied, so the training remains synchronized and free of subtle bugs. Python code, accumulation loop patterns. This script demonstrates how gradient accumulation works by showing simple loop logic that mimics training with a larger effective batch size. Instead of processing a large batch all at once, it accumulates gradients over several smaller steps. The goal is to illustrate the pattern of accumulation and how it scales the effective batch size. The emphasis is on understanding the basic control flow rather than implementation details. The line with the exclamation mark and the pip install command is a shell command meant to install TensorFlow version 2.20.0. It is commonly used in environments like Jupyter Notebooks to make sure the correct TensorFlow version is available for the code to run. In this case, the line is commented out, so it does not actually execute. It is likely kept in the script as a note or instruction for users to manually install that specific version if they need to. We begin by importing a few key Python libraries. The operating system library is included for potential interaction with the system environment, even though it is not directly used here. We also import the random library to help control and generate random values, which is important for making the script's behavior reproducible. Finally, we bring in NumPy, a numerical computing library that we will rely on heavily for working with arrays and performing mathematical operations throughout the code. We begin by importing TensorFlow, a powerful library used for machine learning and deep learning. This import gives us access to tools for building models, running computations, and handling data pipelines. We also check the TensorFlow version to make sure it is compatible with the rest of our code. Knowing the version helps us use the correct features and benefit from any fixes included in that release. We set a fixed seed value so that all random operations give the same results every time the code runs, which is essential for reproducible experiments. This involves assigning the same seed to the random module, to the random number generator in NumPy, and to TensorFlow's random operations. Using a consistent seed across these libraries keeps results uniform between runs, making it easier to debug and to compare different experiments. This line displays the version of TensorFlow currently in use. It provides a quick check that your environment has the correct version of the library installed. Confirming the version helps ensure compatibility and that your code will run as expected. The code checks what kind of device is available by asking TensorFlow for all physical devices that are recognized as graphics processing units. It then sees whether this list is empty or not. If at least one graphics card is found, it sets the device type to GPU. If none are found, it sets the device type to CPU. This tells you whether your computations will run with GPU acceleration or only on the processor. This code reports whether TensorFlow is using a GPU or a CPU for its computations. It first checks if any physical GPUs are available on the system. Based on this check, it sets a variable to indicate the device type. It then prints this information so the user knows which hardware is running the TensorFlow operations. We begin by setting up a small synthetic dataset for a regression problem. The dataset contains 64 samples, each with 10 input features. These feature values are generated using a random number function that produces normally distributed data. We also specify that the data should use the float32 type, so it will work smoothly with TensorFlow operations later in the script. To create a simple linear target variable, We first define the true weights as a sequence of numbers from 1 up to the number of features. We then multiply the input data by this weight vector to compute the target values. After that, we add a small constant of 0.1 to each result to introduce a slight bias. This process produces a synthetic dataset with a clear linear relationship between inputs and outputs, making it well-suited for regression tasks. We begin by placing our input features and target values into a TensorFlow data pipeline. We create a dataset and set a batch size of 4, so each batch contains 4 samples. The dataset is then shuffled using the total number of samples as the buffer size and a fixed random seed to keep results reproducible. This configuration prepares the data for efficient, well-mixed loading during training. The dataset is split into small batches per device, with each batch containing a fixed number of samples equal to the base batch size. This batching makes training on large datasets more efficient and manageable. When the option to drop the remainder is set to true, any leftover samples that do not fill a complete batch are discarded. This ensures that all batches have the same size, which is important for parallel processing and for keeping the training loop consistent. We build a simple linear regression model in TensorFlow using the Keras sequential API, where layers are stacked in order. In this case, we use a dense layer with a single output unit, which is standard when predicting a continuous value. We set the input shape to match the number of features in the dataset, so the model knows the size of the input it will receive. With this setup, the model can learn a linear relationship between the input features and the target variable. We use a stochastic gradient descent optimizer with a learning rate of 0.01 to train the model. This optimizer updates the model's parameters to reduce the loss function. The relatively small learning rate makes these updates gradual, which helps the training process converge more steadily and reliably. We use TensorFlow's mean squared error as our loss function to evaluate how well the model's predictions match the true target values. It does this by taking the differences between predictions and targets, squaring them, and then averaging those squared differences. This loss is widely used for regression problems and provides a clear signal for the optimization process. By minimizing this value, we guide the model to reduce its prediction errors over time. In this example, we simulate training on 2 devices to see how batch size changes. The world size is set to 2, meaning the work is split across 2 devices in parallel. Each device processes a batch equal to the base batch size. By distributing the same batch size to both devices, the overall effective batch size increases, showing how parallel processing can scale training. We use 4 accumulation steps during training, which means we collect gradients from 4 mini-batches before updating the model's weights. This effectively simulates a larger batch size, leading to more stable weight updates and potentially better convergence. It achieves these benefits without needing the extra memory that a true larger batch would require. To find the effective batch size in a distributed training setup, multiply the batch size used on each device by the total number of devices and by the number of gradient accumulation steps. This product gives the total number of samples that are effectively processed together before the model parameters are updated. Understanding this value helps you reason about how much data influences each optimization step in your training process. We first report the per-device batch size, which is how many samples each device processes at once. We then give the world size, meaning how many devices are working in parallel in the distributed setup. Next, we state the number of accumulation steps, or how many mini-batches are processed before the model weights are updated. Finally, we compute the effective batch size as the product of these 3 values, which tells us how much data is used in total before each weight update. To set up gradient accumulation, we first create zero-valued tensors that match each trainable variable in the model, which act as buffers to store gradients over several steps. We also initialize a counter to track how many accumulation steps have been taken so far, so we know when it is time to apply the stored gradients to update the model. Finally, we set the number of training epochs to 1, meaning the training loop will pass through the dataset a single time. We run a training loop for a set number of epochs, and in each epoch, we iterate over the training dataset step by step. At every step, we use an enumerator to track the current step number, while we retrieve a batch of input features and their target values. Processing the data in these smaller batches makes it easier to handle the dataset efficiently and supports gradient accumulation during model training. Before using each batch of data, the code checks that the number of samples matches the expected batch size for each device, and that each sample has the correct number of features. These checks confirm that the data is properly partitioned and that its structure is consistent with what the model expects as input. By asserting these conditions, the training loop can quickly detect and report any unexpected changes in data shape, preventing subtle errors later in processing. We use TensorFlow's gradient tape to record the operations needed for automatic differentiation, so we can later compute gradients. Within this recording context, we pass the current batch of input data through the model with training mode enabled to apply any training-specific behavior. We then compute the loss by comparing the model's predictions to the true target values using the mean-squared error loss function. Before this comparison, we squeeze the predictions so they have the correct shape for the loss calculation. The code uses TensorFlow's automatic differentiation to compute how the loss changes with respect to each trainable parameter in the model. By tracking operations on tensors, TensorFlow can efficiently calculate these gradients. The gradients indicate how much each parameter should be adjusted to reduce the loss. This information then guides the optimization process during training. The code divides each gradient by the number of accumulation steps, so that the result represents an average rather than a total sum. By averaging the gradients over several mini-batches, the update reflects the typical effect of those batches. This helps keep the optimization process more stable and prevents overly large updates to the model's parameters. The code updates the accumulation buffers by adding in the newly computed scaled gradients. It does this by going through each pair of accumulated and scaled gradients and combining them. This refreshes the stored gradients with the latest information. After that, it increases the accumulation step counter by 1 to record that another mini-batch has been processed in the current accumulation cycle. This line checks whether the current step in gradient accumulation has reached the predefined number of accumulation steps. When the count matches this target, it means the accumulated gradients are ready to be used to update the model's weights. This condition ensures that the optimizer only performs an update after a set number of mini-batches have been processed. In effect, it allows training to simulate using a larger batch size without actually loading that many samples at once. The optimizer uses the accumulated gradients to update the model's trainable variables in a way that reduces the loss. Instead of updating after every small mini-batch, it combines gradients from several mini-batches before taking a step. This effectively simulates training with a larger batch size. As a result, the training process becomes more stable and can be more efficient. The code clears the gradient accumulation buffers by creating new tensors filled with zeros for each trainable variable in the model. This removes any previously accumulated gradients after they have been applied. It also resets the accumulation step counter to 0. Together, these actions mark the start of a new gradient accumulation phase and ensure that no old information carries over. To evaluate the trained model, we first run it in evaluation mode on the entire dataset, so its weights are not updated. We then compare its predictions with the true target values and compute the final loss using the mean squared error measure. Finally, we convert this loss into a standard Python number, so it is easier to read and use in later analysis. This code reports the final training loss after using gradient accumulation, giving a clear summary of how well the model trained. It rounds the loss to 4 decimal places to make the result easier to read and interpret. By printing this value at the end of the training loop, it also confirms that the gradient accumulation pattern was applied correctly throughout training. This script shows how to use gradient accumulation in a simple linear regression model built with TensorFlow. It first fixes random seeds for reproducibility, then creates a synthetic dataset with a linear relationship and defines a small model trained with mean squared error loss. The key idea is to accumulate gradients over several mini-batches before updating the model weights, which effectively simulates training with a larger batch size without needing more memory or additional devices. Gradients from each mini-batch are scaled, added together, and used to update the weights only after a set number of accumulation steps. After one training epoch, the script evaluates the model on the full dataset and reports the final training loss, illustrating how gradient accumulation can support larger batch training and potentially better convergence on limited hardware. Learning rate scaling. Changing the effective batch size in distributed training does more than affect speed. It changes the optimization behavior and often requires adjusting the learning rate to stay stable. Larger batches give a more accurate gradient, so you can usually use a higher learning rate without causing divergence. When you simulate large batches with gradient accumulation on limited hardware, the old learning rate may become too small or too large, slowing training or making it unstable. Understanding how batch size, gradient noise, and learning rate interact explains why a setup that works on a single GPU can become unstable when scaled to multiple devices with a larger batch size. When changing batch size, use simple learning rate rules as flexible starting points, not strict laws. If you double the batch size, you can try doubling the learning rate, then watch the loss and validation metrics to see if training stays stable. This often works for large datasets, but smaller or more complex ones may need more cautious changes. Always run short tests first, so you can safely fine-tune the learning rate for your specific workload before committing to long training runs. When using larger batch sizes, start with a simple learning rate scaling rule, then adjust it during training. Use a warm-up phase where the learning rate increases gradually so the optimizer can adapt and avoid early instability. After warm-up, apply a decay schedule to reduce the learning rate over time, which helps maintain good generalization and avoids sharp, unstable minima. In practice, such as training language models on multiple GPUs, combine these strategies with careful monitoring of training loss and validation accuracy to keep learning stable and effective. Python code, learning rate scaling. This script demonstrates how learning rate scaling works by comparing training with small and large effective batch sizes. It focuses on how simple gradient descent behaves under these different conditions. By observing the changes, you can see how batch size and learning rate interact to influence the optimization process. The commented line is instructing you to install TensorFlow version 2.20.0. This sets up the environment with a specific TensorFlow version so it matches what the rest of the script expects. Specifying the exact library version helps prevent problems that can occur when updates change how the library works. We begin by importing several key libraries that the script will rely on. The operating system library lets us work with files and environment settings, while the math library provides common mathematical functions and constants. The random library is used to generate random values and perform random operations. Finally, we import NumPy, which is essential for efficient numerical work with arrays and matrices. Together, these imports provide the basic tools needed for handling data, performing calculations, and supporting the script's main tasks. We start by importing TensorFlow, a widely used library for machine learning and deep learning. After that, we check and print the TensorFlow version currently in use. Knowing the exact version is important because different versions can have different features or behaviors. This helps ensure that the rest of the code will run correctly and be compatible with the installed TensorFlow setup. We begin by setting a seed value, such as 42, so that all random operations give the same results every time the code runs. We apply this seed to Python's built-in random number generator, then to NumPy's random generator, and finally to TensorFlow's random generator. Using the same seed across these libraries makes the behavior of random numbers deterministic. This consistency is essential for reproducibility, debugging, and reliably comparing results across different runs. We define a simple quadratic loss function that measures how far a variable is from the value 3. It does this by taking the difference between the variable and 3, then squaring that difference. Squaring ensures the loss is never negative and makes larger errors count more than smaller ones. In optimization problems, we adjust the variable to minimize this loss, effectively pushing it closer to the target value of 3. The gradient function, called gradFn, computes the analytical gradient of a loss function for a given parameter value x. It does this by taking 2 times the difference between x and 3. The result tells us how the loss changes with respect to x and indicates the direction and size of the update needed. This gradient is then used during gradient descent to move x toward the value that minimizes the loss. We use a function from the numerical library to create a synthetic batch of target values, forming an array of 32 elements where each value is 3. This gives us a simple, uniform set of targets to work with. By keeping all target values the same, we can more easily simulate and analyze how gradient descent behaves during training. This consistent setup helps focus on the optimization process without variation in the training examples. Before training begins, the code checks that the batch of target values has the correct shape. It confirms that there are exactly 32 elements, matching the expected batch size, and that the batch is one-dimensional. These checks ensure the data has the structure that later operations rely on. By catching shape mismatches early, they help prevent errors during the training process. The function defines a simple gradient descent routine that takes an initial value, a learning rate, a batch size, and a number of steps. It initializes the parameter as a TensorFlow variable so it can be updated during training, and creates a list to record the loss at each step. The function then loops for the given number of steps, and in each iteration, it computes the starting index of the mini-batch based on the step number and batch size, wrapping around when it reaches 32 targets. It sets the ending index as the start plus the batch size, and selects that slice of the true targets as the current mini-batch for the update. We start by computing the mean of the current batch using a numerical mean function, which gives the average value of the batch. We then adjust the input to the loss function by subtracting the difference between this batch mean and the target value of 3. This step effectively recenters the batch around 3. Finally, we compute the loss on this adjusted input to measure how far the current value is from the desired target. The code first computes the gradient of the loss with respect to the current value of the variable, which gives the direction and rate of change of the loss. It then updates the variable by subtracting the learning rate times this gradient, moving it in the direction that reduces the loss, which is a standard gradient descent step. After each update, the current loss is converted to a regular Python number and stored in a history list to track how the loss changes over time. In the end, the function returns the final value of the variable as a float, along with the recorded loss history. We begin the gradient descent process by setting the parameter x to 0 as the starting point. We then choose two different batch sizes to compare their effects on learning: a small batch of 4 samples and a larger batch of 16 samples. Finally, we decide to run the gradient descent for 20 steps, meaning we will update the parameter x 20 times during the optimization. We begin by setting a base learning rate of 0.05, chosen to keep training stable with a small batch size. When we switch to a larger batch size, we scale this learning rate by multiplying it by the ratio of the large batch size to the small one. This proportional scaling adjusts the learning rate to match the new batch size while preserving similar learning behavior. In this way, the training dynamics remain effective as the batch size changes. We run gradient descent starting from an initial value of x equal to 0, using the base learning rate and a small batch size of 4 for 20 update steps. The procedure returns the final value of x after these steps and a record of how the loss changes over time. We store these results so we can examine how using a small batch size with the base learning rate influences how well and how quickly gradient descent converges. We now run gradient descent training with a larger batch size and a learning rate scaled up in proportion to that batch size. Starting from an initial parameter value of 0, we use a batch size of 16 and perform 20 update steps. This setup lets us see how scaling the learning rate to match the larger batch affects how quickly and smoothly the method converges. The training procedure returns the final parameter value and the sequence of loss values over the steps, which we use to compare how effective learning rate scaling is across different batch sizes. We compare two gradient descent configurations by printing their key settings and results. First, we report the small batch size and its learning rate, then the large batch size with its scaled learning rate. We also show the final value of the parameter x after training with the small batch, rounded to 4 decimal places, and do the same for the large batch. This side-by-side comparison highlights how different batch sizes and learning rates affect the convergence of gradient descent. We first record the initial loss for the small batch run to establish a baseline, then record its final loss after training to see how much it has decreased. We repeat this process for the large batch, capturing both its initial and final loss values. Comparing these starting and ending losses for both batch sizes lets us evaluate how well the learning rate scaling works. This sequence shows how each configuration performs from beginning to end. The final printout shows that both training setups, even with different batch sizes and learning rates, converge to the same optimal value where x equals 3. This means that when the learning rate is scaled appropriately, both small and large batch configurations can reach similar solutions. Overall, it highlights that proper learning rate scaling is effective for achieving convergence in gradient descent. This script uses TensorFlow to demonstrate how scaling the learning rate in gradient descent can compensate for changes in batch size. It optimizes a simple quadratic loss with an analytically computed gradient, starting from 0 and using a fixed random seed for reproducibility. The procedure is run twice, once with a small batch size and a base learning rate, and once with a larger batch size and a proportionally increased learning rate. In both cases, after the same number of steps, the parameter moves toward the target value of 3 and the loss decreases. The printed initial and final losses confirm that both configurations converge effectively, showing that learning rate scaling can preserve convergence behavior when batch size changes. Mixed precision with DDP. Autocast with DDP. Autocast is crucial for using mixed precision correctly in distributed training of large models. It automatically chooses lower precision for safe operations while keeping important ones, like reductions and normalizations, in full precision. This keeps all model replicas aligned numerically across devices, which is necessary for consistent gradient averaging. By relying on autocast instead of manual tensor conversions, you get a scalable and reliable training setup that extends smoothly from a single GPU to many GPUs. When using autocast with distributed data parallelism, each process independently enters the mixed precision context during its forward pass, combining half and full precision for its own computations. Because autocast behaves deterministically for the same model and inputs, all replicas act the same without extra coordination. This is especially helpful for complex models with operations like convolutions and attention, where some parts are safe in half precision and others need full precision for numerical stability. For example, convolutions can run in half precision to exploit tensor cores, while sensitive operations such as softmax stay in full precision. As a result, gradients reduced across multiple GPUs remain consistent, preserving both performance and reliable convergence. When using autocast in distributed training, you should think about the whole path from inputs to loss and how precision affects communication between processes. Inputs begin in full precision, are automatically converted where helpful inside the autocast region, and then outputs and the loss are kept in full precision to stabilize gradients. This mixed precision approach reduces memory use and speeds up matrix operations, while still ensuring accurate gradient exchange. Because autocast works cleanly with collective operations and keeps gradient types consistent, it provides a reliable way to scale distributed training without harming model quality. Python code, autocast with DDP. This script demonstrates how autocast works in a distributed data parallel style setting. It uses simple tensors to simulate distributed mixed precision rather than focusing on real-world performance. The main goal is to help you understand the behavior of autocast in this context, not to optimize or benchmark speed. This part of the code reminds you that PyTorch must be installed to run mixed precision and distributed data parallel examples. If you are using the script outside a prepared environment, you may need to enable the installation command. Doing so makes sure that PyTorch and its related libraries for vision and audio are available. With these components installed, the script can execute correctly. We begin by importing a few standard libraries to prepare our environment and support reproducible results. The operating system library lets the script interact with the underlying system. The random library is used to generate random numbers, and importantly, to set seeds so that results are consistent across different runs. The math library provides common mathematical functions and constants, and while it is not heavily used here, it is included for completeness and possible future needs. We begin by importing the main PyTorch library to work with tensors, automatic type handling, and device management. We then import the neural network module, which provides the core components needed to build and train neural network models. Finally, we bring in the optimizer module, which supplies algorithms for updating model parameters during training. Together, these imports prepare the environment for creating and training models using PyTorch. We begin by setting deterministic seeds using both the random library and the manual seed function in PyTorch. This makes all random operations produce the same results each time the code runs. Ensuring this repeatable behavior is essential for reproducible experiments and reliable debugging. It allows us to consistently replicate model behavior and any stochastic processes, which helps in tracking down issues and verifying results. This code chooses which device to use for computations by first checking whether a GPU with CUDA support is available. If a compatible GPU is found, it selects the GPU to take advantage of faster processing. If no GPU is available, it falls back to using the CPU. This approach lets the same code run efficiently on different hardware setups while automatically using the best available option. This line reports the version of PyTorch you are using and which device is selected for computation. The device may be a graphics processor if one is available, or it will fall back to the central processor. Checking this information helps you confirm that your environment is set up correctly, which is especially important when using features like mixed precision that rely on specific hardware support. This code defines a tiny model class that extends the standard neural network module in PyTorch to represent a small replica model for distributed data parallel training. In its initialization, it builds a simple two-layer network using three size parameters: input dimension, hidden dimension, and output dimension. The first layer maps inputs to the hidden dimension with a linear transformation, followed by a rectified linear unit activation. The second layer then linearly maps from the hidden dimension to the output dimension. The forward method specifies that an input tensor is passed through the first linear layer, then the activation, then the second linear layer, and the final tensor is returned as the model's output. The initialization method creates a simple two-layer neural network by first calling the parent class initializer, so it inherits all necessary properties. It then sets up a first fully connected layer that converts the input dimension to a hidden dimension. A ReLU activation function is applied next to introduce nonlinearity. Finally, a second fully connected layer maps the hidden dimension to the output dimension. The forward method describes how the model turns input data into an output. It first sends the input through a fully connected layer that transforms it using learned weights and biases. Then it applies a rectified linear unit activation, which introduces nonlinearity by setting negative values to 0. Finally, it passes this result through a second fully connected layer to produce the model's final prediction. This sequence of layers and activation forms the core of the model's prediction process. We create two instances of a simple neural network class called TinyModel to mimic two separate processes in a distributed data parallel setup. One instance represents model rank 0, and the other represents model rank 1. Both models use the same input, hidden, and output dimensions of 4, 8, and 2. After creating them, we move each model to the available device, such as a GPU or otherwise the CPU. This gives us two independent replicas that can be trained separately and then compared, simulating distributed training. We load the state dictionary from the first model into the second model, so both replicas start with exactly the same parameters. This creates identical initial conditions, which is important for consistent behavior in distributed training. With matching starting points, any differences in their outputs or behavior can be traced to the training process itself, not to variations in how the models were initialized. For each model replica, we create a simple optimizer using stochastic gradient descent from the PyTorch optimization module. This optimizer updates the model's parameters during training using a learning rate of 0.1, which sets the step size for each update. By giving each replica its own optimizer, we allow them to update their parameters independently based on their own gradients, which mimics the behavior of distributed data parallel training. We begin by creating a small batch of input data using a PyTorch random function to generate a 2x4 tensor, which represents 2 samples with 4 features each, placed on the chosen device such as a CPU or GPU. We then define the corresponding labels as a tensor containing the integers 0 and 1, indicating the target class for each sample. These labels are also moved to the same device, so they are compatible with the inputs during model training. The code first checks that the input data and labels have the correct shapes before they are used by the model. It confirms that the input tensor has 2 rows and 4 columns, matching the expected dimensions, and that the labels tensor contains 2 elements, 1 for each input sample. By validating these shapes, the code helps avoid unintended broadcasting and other shape-related errors. This ensures that the data is processed correctly and the model behaves as intended. We use a cross-entropy loss function from the neural network module in PyTorch to measure how different the model's predictions are from the true labels. This loss is computed in full precision so that the calculation stays accurate, even if other parts of the model use mixed precision for speed. Keeping the loss in full precision helps maintain stable and reliable training behavior. We use a gradient scaler from PyTorch's automatic mixed precision tools to keep training stable when working with lower precision data types. When a GPU is available, this scaler is enabled and safely scales the loss during training. By adjusting the size of the gradients, it helps prevent numerical issues and maintains reliable learning in mixed precision settings. This function runs a single step of mixed precision training for 1 copy of the model. It begins by resetting the optimizer's gradients to 0, because in PyTorch, gradients accumulate by default. Clearing them ensures that each training step is independent and does not reuse gradient information from earlier steps. This setup is necessary for computing accurate gradients in the operations that follow. We use an autocast context so that operations can run in lower precision when the GPU supports it, which reduces memory use and speeds up computation. Within this context, the model processes the inputs and produces outputs. We then compute the loss with a cross-entropy measure to evaluate how well the predictions match the true labels. This approach enables mixed precision training that improves performance while maintaining good accuracy. The code uses a gradient scaler to scale the loss, which is important for keeping calculations stable during mixed precision training. After scaling the loss, it runs backpropagation on these scaled values. This process helps ensure the gradients are computed safely and remain numerically reliable. As a result, the optimizer can use these gradients to update the model parameters effectively. The code uses a gradient scaler to safely perform an optimizer step during training. It first scales the gradients, then checks whether they are finite. If they are valid, it applies the optimizer step to update the model's parameters. This process helps keep updates stable, which is especially important when using mixed precision training. The scaler is updated at the end of each iteration to prepare for the next one. This update is essential in mixed precision training because it adjusts the scaling factor based on the current gradients. By doing so, it keeps the gradients within a safe numerical range and helps avoid overflow or underflow in later steps. This process maintains stability and reliability during training. The code returns the loss value after first detaching it from the computation graph so that no further gradients are calculated from it. This detachment is important because it allows the loss to be used safely for tasks like logging or comparison without influencing the training process. After detaching, the loss is converted into a regular Python number to make it easy to read and print. In this setup, we run a mixed precision training step separately on each model replica. We first apply the mixed precision step to the replica labeled reg 0 using its optimizer. which performs the forward and backward passes with automatic mixed precision for efficient computation. We then repeat the same mixed precision step for the replica labeled rank 1 with its own optimizer. This way, each model's parameters are updated independently while still benefiting from mixed precision training. We first collect all the parameters from the first model replica, detach them from the computation graph so gradients are not tracked, and flatten them into a single long tensor. We then repeat this process for the second model replica, creating another unified tensor of its parameters. With both models represented as comparable one-dimensional tensors, we can directly compare their values. This numerical comparison is essential for checking that the parameters remain consistent across distributed processes. To measure how much two model replicas differ, we compute the maximum absolute difference between their parameters. We first subtract the parameters of the second model from those of the first to get a tensor of differences. Then we take the absolute value of each difference and find the largest value, converting it to a standard Python number. This single value tells us how far the model's parameters have diverged after a training step, which is important for checking consistency in distributed training. We first print the loss from the first model replica after an autocast step, rounding it for readability to see how mixed precision affects performance. We then do the same for the second replica so we can compare their losses directly. Next, we compute the maximum absolute difference between the parameters of the two replicas to check whether they have diverged during training. Finally, we verify that autocast made consistent decisions across both replicas, which matches how distributed data parallel keeps gradients aligned and ensures stable, synchronized training across processes. This script shows how to use mixed precision in a way that mimics distributed data parallel training in PyTorch. It creates two identical tiny neural networks, runs them on available hardware such as a GPU or CPU, and initializes them with the same parameters. A gradient scaler is used to keep mixed precision training numerically stable, while each model processes a small batch of inputs, computes cross-entropy loss, and updates its parameters. After one training step, the script compares the losses and the maximum difference between corresponding parameters. The nearly identical losses and minimal parameter differences demonstrate that the automatic mixed precision decisions are consistent across the two replicas, similar to how distributed data parallel keeps gradients aligned across processes. Per process GradScaler. In mixed precision training with distributed data parallel, each GPU uses its own gradient scaler to safely handle half-precision gradients. The scaler controls how much the loss is multiplied before backpropagation so the gradients stay in a good numerical range. Each process works on its local mini-batch, runs forward and backward passes, and then synchronizes gradients with the others. Because numerical behavior can differ slightly across processes, each one keeps an independent scaling factor rather than sharing a single global value. Each GPU uses its own gradient scaler in a feedback loop to control numerical precision during training. After scaling the loss and computing gradients, the scaler checks for overflow to see if the scale is too high. If there is no overflow, the scale is kept the same or increased to keep gradients well-sized. If overflow occurs, the scale is reduced, and the optimizer step is skipped to avoid damaging the model parameters. Because each GPU adjusts its scale independently, it can handle difficult data locally while keeping overall training stable. Using a separate gradient scaler for each process aligns well with distributed data parallel training, because each process scales and unscales its own gradients before they are synchronized. As a result, the communication step only handles standard gradients and does not need to be aware of mixed precision. In multi-node setups, each GPU can independently adjust its scaling factor as training stabilizes, without extra coordination. This keeps the system modular and robust, while still achieving efficient gradient aggregation, high throughput, and stable convergence. Python code. Per process GradScaler. This script gives a conceptual demonstration of per process gradient scaling. It simulates two separate processes, where each process uses its own gradient scaler. The goal is to illustrate the logic of how gradient scaling can be handled independently in each process, rather than to perform real distributed training. The emphasis is on understanding the idea, not on providing a full production setup. The script contains a commented line that shows how to install the PyTorch library, along with TorVision and TorAudio, using the pip package manager. This line is not meant to run as part of the script itself, but serves as a reminder or instruction. It is useful if you need to set up these libraries to run or modify the script, especially for machine learning tasks that depend on PyTorch. The script starts by importing three standard libraries: random, math, and operating system tools. The random library is used to generate random numbers that add variability or noise to the simulation. The math library provides mathematical functions and is included mainly for possible future use. The operating system library is also imported as a placeholder for any system-level operations that might be needed in a more advanced version of the script. Together, these imports prepare the environment and ensure useful tools are available for the rest of the code. We begin by setting a fixed random seed using the random library so that any random numbers produced by the program are the same every time it runs. This makes the behavior of the code predictable and repeatable. It is especially helpful for debugging and testing because it allows you to reproduce results and track down issues more reliably. We define a helper class called simple GradScaler that is used to scale gradients during computation. In its initialization method, it sets an initial scale value, which by default is 2.0. This value is taken as an input argument and then converted to a floating point number. Doing this ensures the scale is stored with enough precision for later calculations. This method multiplies the loss value by a stored scale factor before backpropagation. By scaling the loss, it adjusts its magnitude to a more suitable range. This helps maintain numerical stability during training and supports more reliable gradient calculations. This part of the code defines a method in the simple GradScaler class that takes a gradient value and reverses the earlier scaling. It does this by dividing the gradient by the current scale factor. As a result, the gradient is restored to its original size before scaling. This step is essential to ensure that gradient updates during training remain accurate. This function adjusts a scaling factor based on whether an overflow occurs. When overflow is detected, it cuts the scale in half, but never lets it drop below 0.125, so it does not become too small. When there is no overflow, it doubles the scale, but limits it to a maximum of 128, so it does not grow too large. This dynamic scaling helps keep the training process numerically stable. This function simulates a single training step by slightly adjusting a base loss value with random noise. It creates a small variation around 0, then adds this variation to the base loss. The adjusted loss is forced to stay at or above a minimum value of 0.01. This models natural fluctuations in training loss while preventing it from becoming unrealistically small. In this part of the code, the locally computed loss, which has already been adjusted with some noise, is passed through a scaling operation provided by the simple GradScaler class. The goal of this scaling is to change the loss magnitude before running the backward pass in the training loop. This is especially important in mixed precision training, where scaling helps control gradient precision. By increasing the effective dynamic range of the gradients, it reduces the chance of numerical instability during training. In this step, the code sets the fake gradient equal to the scaled loss value. This is a deliberate simplification used for the simulation, where the size of the gradient is assumed to match the scaled loss. By doing this, the example can focus on illustrating how gradient scaling works. It avoids the need to run a full backward pass or compute real gradients, while still conveying the main idea. The code checks whether the computed gradient value is greater than a threshold of 10 to detect a possible overflow during gradient calculation. A gradient that is too large signals an overflow, which can harm the stability of the training process. By performing this check, the system can decide if it needs to adjust the scaling factor used for gradient scaling. This helps maintain numerical stability and more reliable training behavior. The code uses the scaler's unscaled gradient method to reverse the earlier loss scaling. It takes the scaled gradient and divides it by the current scale factor, restoring the original gradient values. This prepares the gradients for later steps, such as combining them across different processes. Doing this unscaling correctly is essential in distributed training so that all collective operations work with properly adjusted gradients. The code adjusts the gradient scaler based on whether an overflow occurs during training. If an overflow is detected, meaning the gradient was too large, it reduces the scale by cutting it in half, but never lets it go below a minimum value of 0.125. If no overflow occurs, it increases the scale by doubling it, but keeps it below a maximum of 128. This dynamic scaling helps keep the training process numerically stable, while still allowing gradients to be as large as safely possible. This function returns a dictionary that summarizes a simulated training step. It records the process ID to show which process was simulated, and it reports the local loss, the scaled loss after applying the gradient scaler, and the unscaled gradient after reversing that scaling, all rounded to 4 decimal places. It also includes a Boolean overflow flag that indicates whether the gradient became too large and may have overflowed. Finally, it reports the current scale value of the gradient scaler, also rounded, giving a quick snapshot of the key training metrics and the scalar's state. We create 2 separate instances of a class called simple GradScaler to represent 2 different processes in a distributed data parallel setup. The first instance, acting as rank 0, starts with a scale value of 2, so it initially multiplies any loss by 2. The second instance, acting as rank 1, starts with a scale value of 8 and multiplies its loss values by 8. By giving each process a different initial scale, we can observe how their behavior may diverge over time, mimicking the independent gradient scaling that can occur during distributed training. The base loss value is set to 1.5 as a common starting point for all processes. Using the same initial loss ensures that each simulated process begins under identical conditions. This allows us to see how each process's gradient scaler changes the loss independently. With this setup, we can fairly compare the behavior of different scalars using the same initial loss. We create an empty list to store the outcomes of each simulation step, then run a loop for 3 steps. In each step, we simulate a training update for 2 separate processes that share the same base loss but use different gradient scalars. For the first process, we call the simulation with process ID 0 and the first scalar. And for the second process, we use process ID 1 and the second scalar. We then save the results from both processes together with the current step number in the list. This setup lets us track how the gradient scaling behavior of the 2 processes diverges over multiple training steps. The code first prints a header line to the console that labels each column of the output that follows. These labels identify the step number, process ID, loss, unscaled gradient, overflow status, and the current scale value. By clearly naming each column, the header helps you interpret the simulation results and understand what each piece of printed data represents. The code loops through each entry in the results list, where each entry represents a step with data from two processes. For every step, it prints a summary for the first process that includes the step number, process identifier, loss values, gradient information, overflow status, and the current scaling factor. It then prints a similar summary for the second process. This output makes it easy to track and compare how gradient scaling changes over time for both processes. This script demonstrates a simplified form of per-process gradient scaling using two independent training processes, each with its own gradient scaler. The processes start with different initial scales, then repeatedly apply noise to a base loss value to simulate training variability. At each step, the loss is scaled and checked against a threshold to detect overflow. If overflow occurs, the scale is reduced, and if not, the scale is increased. Over 3 steps, the script shows how each process independently adjusts its scaling factor, illustrating how gradient scaling behavior can diverge across processes in distributed training. The output summarizes, for each step and each process, the loss values, whether overflow happened, and the current scale. Handling overflow errors. When using mixed precision in distributed data parallel training, controlling numerical overflow is essential for stable and effective learning. Mixed precision improves speed and reduces memory use by relying on lower precision, but this also makes gradients more likely to overflow and become infinite or undefined, which can break convergence. In distributed setups, the problem is amplified because many processes compute and synchronize gradients together. So overflow in one process can affect them all. Understanding how and why overflow occurs, how often it appears in mixed precision, and how it impacts distributed systems is key to designing robust training loops that can handle these issues gracefully. Modern training frameworks use gradient scaling to prevent numerical overflow and loss of small gradient values. They do this by multiplying the loss by a large factor before backpropagation and dividing the gradients by the same factor afterward. If an overflow is detected, the update step is skipped and the scale is adjusted for the next iteration. In distributed training, all processes must make the same decision about skipping or applying updates, so the model doesn't diverge. Consistent overflow handling across processes is essential to keep the model correct and avoid subtle bugs. In mixed precision distributed training, you need to carefully monitor and control numerical overflow. Some overflows are normal at the start or with aggressive settings, and the gradient scaler often adapts so they decrease over time. You should log scale factors and skip steps to spot ongoing problems, which can indicate learning rates that are too high or unstable initializations. By detecting and fixing these issues, you can keep the advantages of mixed precision and parallelism without harming model quality. Python code, handling overflow errors. This script provides a simple, conceptual demonstration of how overflow handling works. It simulates how mixed precision computations detect when values become too large to represent accurately. The main goal is to show this behavior in a clear, beginner-friendly way. All printed output is designed to make the overflow detection process easy to follow and understand. This part of the code is reserved for installing any external packages the script needs. Here you would add commands to install required libraries, such as TensorFlow version 2.20. Setting up these dependencies in advance helps ensure that, when you run the script, it has all the necessary components and can execute without errors caused by missing libraries. The script starts by importing 3 key standard libraries to prepare its working environment. It brings in the math library for mathematical functions and constants, the random library for generating random numbers used in stochastic processes or simulations, and the operating system library for interacting with files, directories, and other system-level tasks. Together, these imports enable the script to perform calculations, handle randomness, and manage resources on the computer. We set the random seed to 42 so that any random numbers generated by the script are always the same each time it runs. This makes the sequence of random values reproducible. Reproducibility is important because it allows us to reliably debug and test the script, since results will not change unpredictably between runs. Simple GradScaler is a small class that imitates a gradient scaler used in machine learning to improve numerical stability during training. It stores a scale value and a growth factor as floating point numbers and uses the scale to multiply the loss before the backward pass, so very small gradients are less likely to vanish. A method for scaling the loss simply returns the loss multiplied by the parent scale. Another method checks all gradients for overflow, meaning values that are infinite or not a number. If any overflow is found, it reduces the scale by dividing by the growth factor, but never lets it drop below 1. And if no overflow is found, it increases the scale by multiplying by the growth factor. This adaptive adjustment keeps a balance between precision and numerical range during training. The initialization method for the simple GradScaler class sets up its starting conditions using 2 parameters, an initial scale and a growth factor, both with default values. The initial scale is set to 1024 and the growth factor to 2, and both are converted to floating point numbers for precise calculations. The initial scale defines the starting level for scaling operations, while the growth factor determines how this scale changes over time, allowing the scaler to adjust dynamically during training. This method multiplies the loss value by a scale factor before running the backward pass in training. By scaling the loss, it adjusts its magnitude to better control the numerical behavior of the gradients. This helps maintain numerical stability and precision during gradient computation. This step function checks the gradients for overflow by looking for infinite or not a number values. If an overflow is found, it lowers the scaling factor by dividing it by the growth factor, but never lets it drop below 1. If no overflow is detected, it raises the scaling factor by multiplying it by the growth factor, allowing larger scaling in future steps. It returns true when no overflow occurs and the scale is successfully increased, and false when an overflow is handled by reducing the scale. The code configures a simulation environment with 2 processes, representing 2 distributed data parallel workers in a machine learning setting. Pause. By using 2 processes, it can model how each worker independently handles tasks such as gradient scaling and detecting numerical overflow. Pause. At the same time, the processes run in parallel, mimicking the behavior of real distributed training. Pause. This setup allows the script to test and observe these mechanisms without needing a full multi-machine system. We create a separate gradient scaler for each simulated process by building a list of scalar instances, 1 per process. Each entry in this list is a new simple GradScaler object, giving every process its own independent scalar. This independence is important in distributed training because it lets each process handle overflow based on its own gradient values. As a result, each process can adjust its scaling factor appropriately, which helps keep the training loop stable and efficient. We use a helper function to simulate gradient computation in a controlled way. It first creates a base gradient that grows slightly with each step. then adds a small noise term that depends on the process index to introduce variation between processes. These two parts are combined to form the final gradient value. For one specific case, when the step index is 2 and the process index is 1, the function simulates an overflow by returning a list whose first element is infinity and whose second element is the computed gradient. In all other cases, it returns a list containing the gradient and 1.5 times that gradient, representing a simple gradient computation scenario. Before using the gradients, we first validate their structure for each process. We call a helper function with a fixed step index and the current process index to generate a list of gradients, then confirm that the result is actually a list. We also check that this list has exactly 2 elements, matching the expected format of the gradient data. Performing these checks early helps catch incorrect data types or shapes and prevents errors later in the code. We set the number of loop iterations to 5 to simulate a small, controlled sequence of training steps. This fixed limit lets us clearly observe how the code behaves when overflow occurs. Within these steps, we can track how gradient scaling is applied and how overflow detection responds. Overall, the goal is to study overflow handling in a simple, predictable setting. The code first prints a header line to the console that labels the columns in the output. These columns show the step number, the scaled loss for the first process, the scaled loss for the second process, and whether an update was applied at that step. By defining these labels up front, the program makes it easier to interpret each line of output from the loop that follows. This structure helps the reader track how scaling and update decisions change over the course of the simulation. We simulate a training loop by iterating over a series of steps and computing a loss value at each step. The loss for a given step is set to increase linearly with the step number, creating a simple growing sequence of losses for each process. We then create an empty list to hold scaled losses, and for each process, pass its loss value to the scale loss method of its associated simple GradScaler. This method multiplies the loss by the scalar's current scale factor, and the resulting scaled loss is added to the list for further use in the loop. We begin by setting up an empty list to hold the gradients produced by each process. We then loop over the processes, in this case 2 of them, and for each one we call a gradient simulation function with the current step and the process index. This function returns the gradients for that specific step and process, and we add those results to the list. Organizing the gradients this way lets us examine each process separately, which is important for detecting overflow and adjusting the scaling factor when needed. We create a list to record whether each process is allowed to update based on its gradient checks. Then we loop over all processes, and for each one, call its scalar step method with that process's gradients. This method looks for infinite or invalid gradient values and adjusts the scaling factor if needed. It returns a true or false value, indicating whether the update is safe, and we store this result in the list. In this way, each process independently decides if it can proceed with updating, based on the status of its gradients. The code uses a list of true or false values to represent whether each process can safely apply its update without causing overflow. It then uses a function that checks if all values in this list are true. If every process is marked as safe, the system concludes that all processes can proceed. In that case, it allows the global update to take place. The code decides whether to apply or skip an update based on the status of all processes. It first checks a global condition that combines the local decisions from each process. If every process can safely proceed, it sets the decision text to update, meaning the update will go through. If any process reports an overflow, it sets the decision text to skip, meaning the update will not be applied. This line of output summarizes what happens at each step of the process. It first shows the current step number, then the scaled loss for the first process, and then the scaled loss for the second process, with both loss values rounded to one decimal place. Finally, it prints a short decision message that states whether an update was applied or skipped. Together, these values give a concise view of the scaling behavior and the decision made at each step. The code prints the final scaling factors for each process to show how they have adapted during the simulation. It reads the scale value from each gradient scalar, formats it to one decimal place, and labels the output for each process. This gives a concise summary of how the scaling factors evolved and how overflow was handled over time. This script illustrates how to handle overflow errors in a simplified gradient scaling setup, similar to what happens in mixed precision training. A small class acts like a gradient scaler, increasing the scale when no overflow is detected and decreasing it when overflow occurs. The code simulates two processes over 5 steps, computes scaled losses, checks for overflow, and prints whether each step applies an update. An intentional overflow is triggered at the second step for the second process, causing that update to be skipped. By the end, the final scales for both processes show how the scaler adapts to overflow conditions over time. Robust distributed training, rank-aware logging. In distributed training, rank-aware logging makes each log message clearly indicate which process produced it and what role that process has. As the system scales to many processes, this prevents logs from becoming chaotic and hard to debug. By tagging messages with identifiers such as global rank and node name, and by controlling which processes are allowed to log certain information, it becomes easier to follow what the system is doing. For example, the main process can report overall training progress, while other processes focus on diagnostic details, resulting in a clear and organized view of system activity. When designing rank-aware logging, the goal is to balance how much you log with how responsible each process is for that logging. If every process writes all details to a shared location, storage can be overwhelmed and debugging becomes harder. A better approach is to assign different logging roles to different ranks, such as having the primary process write concise, user-facing updates, while other processes record detailed diagnostics in their own files. In large distributed systems, each node can keep its own log with rank tags, while the primary process maintains a short, easy-to-read log. This structure provides both a clear high-level overview and access to detailed information without creating redundant messages. Rank-aware logging is crucial in distributed systems because it helps detect subtle bugs and performance issues that single process logs can miss. By tagging logs with rank identifiers, timestamps, and key batch or step information, you can trace the exact sequence of events that leads to failures, such as workers hanging during synchronization or gradients exploding on specific ranks. In large-scale training across data centers, these logs reveal patterns like repeated failures or timeouts in certain regions, which enables targeted fixes. Over time, teams refine consistent log formats and filtering practices, so it becomes easier to understand each process's role in complex training runs. Python code, rank-aware logging. This script introduces the basics of rank-aware logging by simulating multiple distributed ranks using simple integer identifiers. Its main goal is to show how to produce clear, concise log messages that indicate which simulated rank they come from. By focusing on rank-specific output, it helps illustrate how logging can stay organized and readable in a distributed setting. In this part, we note that some scripts might need extra software installed, but that is not the case here. This simple example uses only Python's built-in standard library. As a result, the setup stays easy and minimal, and the focus remains on demonstrating the core functionality without relying on any external dependencies. We begin by importing a module that lets us interact with the operating system, which is useful for tasks like working with files or environment variables. We also import the time module so we can use functions related to the current time and formatting timestamps. Finally, we bring in the optional type from the typing module to indicate that a value or function result can either be a specific type or be none, which improves code clarity and type checking. This function creates a formatted string of the current time using the time module. It gets the current local time and then uses a formatting method to convert it into a string showing hours, minutes, and seconds, separated by colons. The result is a clear, human-readable timestamp. This makes it useful as a helper function for consistent timestamps in logging. Rank logger is a class used to manage logging in a distributed system. Its constructor takes three inputs: a global rank that uniquely identifies each process, the world size that gives the total number of processes, and a flag that indicates whether the current process is the primary one. The primary process usually has extra responsibilities, such as coordinating tasks. These values are stored inside the object so they can be used later when producing log messages. This method first decides whether the current rank is the primary process or a worker, and sets its role accordingly. It then builds a prefix string that starts with the current time in hours, minutes, and seconds. After that, it adds the rank information, showing the current rank out of the total world size. Finally, it appends the role, primary or worker, so each log message is clearly labeled with its rank and role. This function logs messages only from the primary rank in a distributed system. It first checks whether the current instance is the primary rank, and if not, it exits without doing anything. If it is the primary rank, it builds a log prefix that includes the current time, rank information, and the primary role. It then prints the full log message by combining this prefix with the given message. So only the primary rank outputs these important logs, and other ranks do not add extra clutter. This function lets any rank in a distributed system write log messages. Each message is printed with a formatted prefix created by a helper method. That prefix adds context, such as the current time, the rank of the process writing the log, and whether it is a primary or worker role. As a result, the logs are clear and informative, making it easy to see exactly where each message originated in the system. This function models a single step in distributed training by computing a simple loss value. It starts from a base loss of 1 and divides it by the step number plus 1, so the loss decreases as training progresses. If this computed loss is 0 or negative, it raises an error because the example assumes the loss must stay positive. Finally, it adds a small amount based on the rank identifier, equal to 1/100th of the rank, to introduce a slight variation between different ranks. This function sets up a simple demonstration of a distributed system using simulated ranks. It takes two parameters: the total number of ranks, called the world size, and the number of steps in the simulation. Both of these default to 3. Before running, it checks that the world size is greater than 0 and raises an error if it is not, so there is always at least one rank. It also verifies that the number of steps is positive, raising an error otherwise, to ensure there is at least one step to execute. These checks prevent invalid configurations and help maintain the integrity of the simulation. We begin by creating a list that will store a logger for each simulated rank in the distributed system. We then loop over all ranks in the world size and check whether the current rank is 0, which identifies it as the primary rank with special logging duties. For each rank, we create a rank logger instance using its rank, the total number of ranks, and whether it is the primary rank. Each logger is added to the list, so they are all ready to use in the distributed training simulation. The code starts by having the primary logger announce the beginning of the training process. It does this by calling the main logging method on the first logger in the list, which represents the primary rank. This message states that a simulated distributed training run is starting and prepares the system for the upcoming steps. Making this announcement is important in distributed settings so that all ranks clearly know when training has begun. The code runs a loop over the training steps, and for each step, it goes through every rank and its logger. It computes the loss for the current rank at that step using a simulated training function. If the logger is for the primary rank, it records a summary message with the step number and the formatted loss. For all other ranks, it logs a message with the local loss for that rank and step. This design lets the primary rank provide an overall summary, while the other ranks report their individual results. In this example, the primary logger, which corresponds to rank 0, prints a message when a checkpoint is saved at the final step. This illustrates how the main process in a distributed training setup is responsible for announcing important events. By logging these key actions centrally, it ensures that critical information is clearly recorded and easy to track. The script ends by running a demonstration function that launches a small distributed training run with 3 ranks and 2 training steps. In this run, each rank performs the same 2 steps, but only the primary rank logs key information. It announces the start of training, reports the loss after each step, and notes when a checkpoint is saved at the end. This simple setup illustrates how rank-aware logging can control what is displayed in a distributed training environment. This script demonstrates a simple distributed training setup with 3 ranks, where one primary rank coordinates logging and checkpointing, while the others act as workers. Each rank is identified by an integer, and the primary rank records key events, such as the start of training and when checkpoints are saved. At each training step, the script computes a loss value that decreases over time, with a small difference for each rank. The primary rank logs an overall loss summary, while the worker ranks log their own local loss values. The example runs for 2 steps to show how logs from different ranks highlight the primary rank's role in summarizing progress and managing checkpoints. Distributed checkpoint design. When designing checkpoints for distributed training, you need more than periodic saves of model weights. All processes across machines must coordinate to create one consistent snapshot of the entire training state. A solid checkpoint includes model parameters, optimizer state, and training progress such as global steps or epochs, and it must match across all ranks. Usually, a single main process writes the checkpoint to avoid race conditions or file corruption. Overall, the checkpoint acts as a contract that lets training resume smoothly after failures or on different hardware setups. In distributed training, checkpoints must capture the full training state, even though different processes hold different parts of the model. Instead of one large file, the checkpoint is split into coordinated pieces. One option is for each process to save its own part, with a central record describing how these parts fit together. Another option is to gather all parameters to a single process for saving, which makes loading simpler but can be slower for very large models. The best approach depends on model size and storage constraints, but the key goal is that any process can restart with exactly the state it needs. In distributed training, checkpoint design focuses on when to save, how to name versions, and how to avoid corrupted files. Checkpoints are usually linked to a shared progress marker, such as a specific optimizer step, so all processes agree on the save point. Including this marker in the checkpoint name makes it easier to choose the correct file when resuming. To prevent partial or corrupted files, systems often write to a temporary location and rename the file only after the save is complete. In cloud environments, a well-designed checkpointing system turns interruptions into minor events, while a poor one can waste resources and force training to restart. Python code. Distributed checkpoint design. This script demonstrates a simple approach to distributed checkpointing. It simulates two worker processes and a coordinator that manages them. The main goal is to show how to safely log progress and save checkpoints in a distributed setting. By focusing on safe logging and checkpoint saving, it highlights the core ideas needed to maintain reliable state across multiple processes. This commented line is a note suggesting the installation of TensorFlow version 2.20.0 to match the version expected by the script. It is there to help avoid compatibility issues, since different TensorFlow versions can behave differently. Because the line is commented out, it indicates that installing this version is optional or that the user is expected to have already done it. We begin by importing three key libraries for our script. Pause. The operating system library lets us work with file paths and directories. Pause. The JSON library allows us to store and load data in a structured format, which is important for handling checkpoints. Pause. Finally, the random library controls random behavior in the code, so that by setting a seed, we can make those random operations consistent and reproducible. We begin by fixing the seed of the random number generator so that any random operations give the same results every time the program runs, which is important for reproducible experiments and easier debugging. We also set the Python hash seed environment variable to the same value so that Python's hashing behavior is consistent across runs. Together, these steps create a controlled and predictable execution environment where results can be reliably repeated. We begin by creating a dictionary that stores the training state of the model. It has two entries, one that records the global step, starting at 0, to count how many training steps have been taken, and another that records the epoch, also starting at 0, to count how many full passes through the training data have been completed. By updating these values during training, we can easily track and monitor the progress of the model over time. We use a dictionary to store the state of a simple model with two parameters called weight and bias, both starting at 0. These values are meant to be updated during training as the model learns. In a basic linear model, the weight represents the slope and the bias represents the intercept. Initializing them to 0 provides a neutral starting point for the training process. We create a small dictionary to store the state of an optimizer, and in this case it holds a single setting called the learning rate, set to 0.1. The learning rate controls how quickly the optimizer updates the model's parameters during training. Keeping this value in a dictionary makes it easy to access, manage, and change the optimizer's settings as training progresses. We first set up a directory called checkpoints demo to store our training checkpoints in one place. This directory is used to save and later retrieve the state of the training process. We rely on the operating system library to create the directory only if it does not already exist, so the program does not fail when it is run multiple times. This simple setup keeps checkpoint files organized and makes it possible to safely save and restore the training state. The rank file name function creates the file path for a specific worker's checkpoint file. It takes the worker's rank and a suffix that usually indicates a particular step or state. Using a path joining method, it combines the checkpoint directory with a file name that includes the rank, the suffix, and a JSON extension. This guarantees that each worker's checkpoint file has a unique name and is saved in the correct directory. The code creates the full path to the checkpoint index file by combining the checkpoint directory with the checkpoint index file name. It uses the operating system tools to safely join these parts into a valid path. This path tells the coordinator exactly where to store the index of all checkpoints, so the file is always saved in the correct directory. This function models a worker process in a distributed training system using two inputs: the worker's rank, which is its unique identifier, and the current training step. Inside the function, it builds a small dictionary called a shard that records the worker's rank, the current step number, and a weight shard. The weight shard is computed as this worker's portion of the model's weight by adding its rank to the current weight value stored in the model state. The function then returns this shard dictionary, which represents that worker's contribution to the overall model state. This function safely writes data to a JSON file by first creating a temporary version of the file. It opens the temporary file with UTF-8 encoding and writes the JSON data to it. After the write succeeds, it renames the temporary file to the original file name, replacing any existing file. This two-step process helps prevent data corruption if something goes wrong while writing. This function saves the state of all workers to disk in a distributed way. It loops over each worker, generates that worker's state using its rank and the current global step, and safely writes this state to a separate file. For each worker, it records the rank and file location in a list of shards. After all workers are processed, the function builds an index that includes the global step, the list of shard entries, and copies of the training and optimizer states. It then safely writes this index to a central file, so the overall training state can be consistently restored later. This function tries to load the most recent checkpoint index from disk. It first checks whether the index file exists, and if it does not, it returns a value indicating that no checkpoint is available. If the file is present, it opens it for reading with the correct text encoding and uses a JSON parser to convert the file contents into a Python dictionary. The function then returns this dictionary so the rest of the program can access the stored checkpoint information. This function rebuilds the full state by loading data from multiple shard files. It starts with an empty list to hold shard data, then goes through each shard entry in the index to get its file path. For each path, it checks that the file exists and raises an error if it does not. If the file is found, it opens it, reads the JSON content, and adds that data to the list. In the end, it returns a dictionary that combines the original index with the list of all loaded shard data. This function simulates distributed style checkpointing during training. For each step in the specified range, it updates the global step in the training state and resets the epoch count to 0. It then slightly increases the model's weight and bias values to mimic a training update. Every 2 steps, it saves a sharded checkpoint using the current step and world size and reports that a checkpoint has been saved at that global step. The function first tries to load the latest checkpoint index using a helper routine, and if none is found, it reports this and exits so no further work is done without a valid checkpoint. When a checkpoint index is available, it restores the full training state from it and prints the global step that was recovered, showing where training can resume. It also reports how many shards were restored to confirm that the distributed state was fully reassembled. Finally, it prints the keys from an example shard to reveal the structure of the restored data and support debugging and inspection of the checkpoint contents. The script first checks whether it is being run as the main program so that certain actions only occur when it is executed directly, not when it is imported. It then sets the world size to 2 worker processes and defines a total of 4 training steps for the simulation. Next, it calls a training function that runs the distributed training process and saves checkpoints at specific intervals. After this simulated training, it calls another function to resume from the most recent checkpoint, demonstrating how the checkpointing system allows the training to continue from where it left off. This script illustrates a simple distributed checkpointing system with 2 simulated workers and a coordinator. Each worker holds a shard of the model state, and during training the model's weight and bias are updated step by step. Every few steps, the system saves a checkpoint that captures the global training state, the optimizer state, and the individual worker shards as JSON files. The script can then resume training by loading the most recent checkpoint and reconstructing the full state from these shards. When run, it prints messages showing when checkpoints are written and when the system successfully restores the last saved global step and shard information. Reliable run recovery. In distributed training, failures such as network issues or memory errors are normal and must be planned for. Reliable recovery means you can pause training, fix the problem, and resume without losing meaningful progress. To do this, you need checkpoints that store not only the model parameters, but also optimizer states, learning rates, and other training details. These checkpoints must be consistent across all processes so that when you restart, training continues smoothly with minimal extra computation. In distributed training, reliable recovery depends on careful checkpoint management. Only one process should write checkpoints, so files are not corrupted, and all processes must agree on the exact training step being saved. It is best to synchronize checkpointing at clear points, such as the end of an epoch, and to write checkpoints atomically, using temporary files so incomplete saves are never used. This ensures that after a failure, the system can safely resume from a complete checkpoint or fall back to an earlier one without damaging model quality. To ensure reliable run recovery, you should regularly test that training can be paused and resumed from recent checkpoints, even after software or hardware changes. This includes simulating failures by stopping a job and restarting it to confirm that metrics such as loss and accuracy stay consistent. It is also important to record detailed metadata with each checkpoint, including configuration and environment information, so runs remain reproducible. With this validated resume process integrated into your workflow, interruptions become manageable, and long distributed training jobs can continue without major setbacks. Python code, reliable run recovery. This script demonstrates the basics of reliable run recovery in a training workflow. It simulates how to create checkpoints and safely resume runs, emphasizing proper logging and atomic saving of checkpoint data. The goal is to ensure that if a run is interrupted, it can restart without losing progress or corrupting saved state. It uses a specific version of TensorFlow to support these behaviors consistently. We start by importing 3 standard Python libraries that support key tasks in our program. The operating system library lets us interact with the system, especially for working with files and directories. The JSON library allows us to convert Python data to and from JSON format. The random library provides tools for generating random numbers, so we can add controlled randomness and set seeds for reproducible results. TensorFlow is a powerful library used for machine learning and deep learning tasks. In this script, it is imported to build and train a simple neural network model. This import is necessary because it provides the tools to define models, add layers, and run training routines. Without TensorFlow, these core functionalities for creating and training the example model would not be available. We control randomness in our code to make results reproducible. First, we set a fixed random seed using the standard random library so that any random operations behave the same each time. We also set a specific value for the Python hash seed through an environment variable to keep Python's hashing behavior consistent. Finally, we set TensorFlow's random seed so that its internal randomness, such as weight initialization and data shuffling, is repeatable. Together, these steps create a predictable environment that allows experiments and training runs to be reliably repeated. We first set up a main directory called Reliable Run Demo, which will act as the root location for all our training checkpoints. Inside this main folder, we then define a dedicated checkpoint subfolder. Organizing checkpoint files in this single, clearly named subdirectory keeps them easy to manage, locate, and reuse during training. The code uses the operating system tools to create a directory where model checkpoints will be stored. It sets a path for this checkpoint folder and makes sure it exists, creating it if necessary. This prepares a dedicated location for saving model states during training. With these checkpoints in place, training can resume from the most recent saved state if it is interrupted. This helper function prints a short header that shows which version of TensorFlow is currently being used. It reads the version information directly from the TensorFlow library. Knowing the exact TensorFlow version helps with compatibility checks and debugging, since different versions can behave differently or support different features. We define a simple neural network model using the Keras interface in TensorFlow. It takes 28 by 28 pixel MNIST images as input, flattens them into a one-dimensional array, then passes them through a dense layer with 32 neurons using the ReLU activation to add nonlinearity. The output layer has 10 neurons with a softmax activation to produce class probabilities for the 10 MNIST digits. The model is compiled with the Atom optimizer, using a small learning rate, sparse categorical cross-entropy as the loss for multiclass classification, and accuracy as the performance metric. The function returns this compiled model ready to be trained on data. This function quickly prepares a small subset of the MNIST dataset for testing. It loads the training images and labels using TensorFlow's dataset tools, then selects a specified number of samples. The image pixels are normalized to floating point values between 0 and 1, and the labels are converted to integers so they work properly with the model. It then returns these processed images and labels, ready to be used for training or evaluation. This function builds a dictionary that records the current state of a training run. It takes the current epoch, the current step, and the training history as inputs. The epoch and step values are converted to whole numbers. The history, which tracks metrics such as loss and accuracy over time, is stored directly. The resulting dictionary can then be used to save or restore the training state later. This function saves a model checkpoint in a safe, all-or-nothing way. It first writes the model's weights and the training state, such as the current epoch and step, to temporary files. Once both temporary files are fully and successfully written, it renames them to their final checkpoint locations using an atomic replace operation provided by the operating system. This prevents partially written or corrupted checkpoints. In the end, the function returns the path to the completed checkpoint file so it can be used later. This function tries to restore a model from a saved checkpoint. It first builds the expected locations of the model's weight file and its separate state file, then checks whether both exist. If either file is missing, it returns nothing, meaning there is no valid checkpoint. If both are present, it loads the model's weights, reads the state file, parses it as JSON, and returns the recovered state so training can continue from where it previously stopped. This code sets a flag to indicate that the script is acting as the main process in a distributed training setup, even though it is actually running as a single process. By doing this, it simplifies the logic that would normally handle multiple processes. It assumes that only this main process is responsible for tasks such as saving checkpoints. As a result, only one instance performs these special actions, which prevents conflicts and avoids doing the same work more than once. This function prints the TensorFlow version, loads a small MNIST training set, and builds a simple neural network with the Keras interface. It sets up a checkpoint location, then tries to load any existing checkpoint so training can resume from the last saved epoch. Otherwise, it starts fresh. The training data is turned into a shuffled and batched TensorFlow dataset, and the model is trained over several epochs, beginning from the saved epoch if one exists. For each epoch, it trains on a fixed number of batches, records loss and accuracy, and skips any empty batches. After each epoch, if running as the main process, it atomically saves the current training state and model weights, then reports that the checkpoint was saved, and finally prints how many epochs are stored in the training history. This script shows how to build a reliable run recovery system for training a TensorFlow model. It uses a simple neural network on a small part of the MNIST dataset and focuses on safely resuming training from checkpoints. The script sets deterministic seeds for reproducibility, then checks for existing checkpoints to decide whether to continue training or start from scratch. At the end of each epoch, it atomically saves the model weights and training state, so that if interrupted, training can restart from the last saved point. It also logs loss, accuracy, and the number of completed epochs, ensuring progress is preserved without data loss. In this lecture, you learn to apply gradient accumulation and effective batch size strategies in distributed training setups, combine mixed precision with DDP to improve throughput while maintaining convergence, and implement basic logging and checkpointing that work correctly in multi-process environments. In the next module, Module 9, we will go over export and deployment.
Thank you for your attention. See you all in the next lecture.